we left off last time talking about what it means when we talk about the voltage of a system. That voltage is also known as the potential difference. And there are 5 different ways that that could be referred to in an AP Chemistry question. And so I want you to be familiar with these to the point that you know if it asks for any of these, it is asking us for the voltage. So first off, if it asks you for the EMF, that is the electromotive force, or the force that's causing these electrons to move. That force is caused by the difference in energy between the anode and the cathode. So that is also simply the voltage. The standard EMF, that is again the electromotive force, but it's just specifying the conditions. So for the standard EMF, we need our temperature to be 25 degrees Celsius. We're going to have 1 molar concentration for anything in solution and 1 atmosphere of pressure for anything that is a gas. Also, this could be written as E, standing for that electromotive force, cell. Okay, that's our cell potential. Or the same thing, E cell with that standard symbol. Same thing, except now you're specifying the temperature, the concentration, and the pressure under those conditions. And this also could be referred to simply as the cell voltage. So if they ask you for any of these things, they're asking us to find the voltage of the system. Right, this slide summarizes the conditions that we need for standard cells. So in this section, we're only going to talk about standard cells. So we need our concentrations to be 1 molarity. Our pressures, if we have any gases involved, are going to be 1 atmosphere, and then we'll keep the temperature at 25. If any of these conditions change, it can change the voltage of the system. So that will make a little bit more complex problem. So for now, we'll just focus, okay, what if we have a standard system? There is a chart that has been created for the standard reduction potential of a variety of species. Really almost anything you can think of. And so that's why we want to focus on standard cells first, because the standard cell potential, right, the potential energy for those cells has already been determined. We can then use these standard potentials for the anode and the cathode to calculate the overall voltage or overall potential of our complete cell. So the standard potentials for half cell reactions are used to calculate the standard cell potential for the overall reaction. By convention, all standard half cell potentials are given as reduction potentials. So they've already determined the potential energy for all of the metals that we could use, as well as some nonmetals that we could use as our cathode and as our anode. They are writing them, though, in the half. So here's the cathode half, here's the anode half. However, they're all written as though they were being reduced, reduction potentials. So on the chart, we'll see, for example, if copper plus 2 gain 2 electrons to become copper solid, that has a potential energy of 0.34 volts. But remember that only the one at the cathode is actually being reduced, the one at the anode is being oxidized. However, they're all written as though they were being reduced. So we'd have to flip it around if it was being oxidized. So that would be copper goes to copper plus 2 plus 2 electrons. What do you think would happen to this potential energy if we flip that around? Well, instead of 0.34 volts, it would be negative 0.34 volts. here are some values that they've already figured out for the reduction potential of some various metals. And these are listed in order from highest to lowest for this set. So you can see up here that silver has a high potential to be reduced, as does iron, iodide, copper +2, so on and so forth. If we get down to something like aluminum +3, it has a pretty low potential, actually a negative potential, to be reduced. That probably means that the reverse reaction would be preferred for aluminum. Okay, so what you would do if you had two metals and you were trying to make a cell, let's say you wanted to use silver and nickel. Remember, one of them has to be reduced and the other one has to be oxidized. So which one do you think, silver or nickel, is more likely to be reduced? Well, it's the one with the higher reduction potential. So silver has a higher reduction potential, so it's more likely to be reduced. Nickel has a lower reduction potential, so it's more likely to be oxidized. So the silver would probably be our cathode, and it would be reduced, and the nickel would probably be our anode and get oxidized instead. To figure out the voltage on the whole system, we would flip this number, because we're going to flip this reaction, because it's going to be the anode. So that'd be positive 0.25 volts, and then we put these together to find the potential energy of the system. So the potential energy is the difference between 0.8 and negative 0.25, but if you subtract a negative, that's a positive. So this is a 1.05 volt system, if we put those together. That's just a random example. Let's see what examples they want to throw at us next. Alright, we're going to annotate this chart just a little bit more. If we look over here on the left, these are the species that are being reduced because they're having electrons added to them. And as we go up, there is increasing ability to attract electrons or to get reduced. However, over here on the left, if we flip these reactions around, okay, think about if all these got flipped around, then these would be being oxidized. So they'd be losing electrons. When we do that, we would flip these numbers around. So then this one would be the highest if we flip them. So that means this is the most able to lose electrons. So as you go down, they become easier to oxidize the products. And as you go up, it becomes easier to reduce the reactants. So remember, reactants are being reduced, and if we flip it, products are being oxidized. And these numbers tell us their ability to do one or the other. So if we have a cell, and we have two metals, which one will be reduced? They can't both be reduced, right? One of them's got to be reduced, one of them's got to be oxidized. So the one with the most positive or least negative, if they're both negative, will be reduced because it has the greatest ability to attract electrons. The electron, remember, is only going to move where it can decrease its energy. And so the only way the electron can decrease its energy is by moving from the most positive, least negative potential value. Okay? Excuse me, moving to. So the electron's going to move to the one that has the most positive potential, because that is saying it is most likely to be reduced. Alright, so then how do you figure out the potential for both of them? Well, you take the one that's being reduced, and then you find the difference between it and the one that's being oxidized. Because you're finding the difference, you change the sign on the one that's being oxidized. So you can say cathode minus anode, or another way to say that is cathode plus anode, but you change the sign on the anode. In this case, what's happening is your cathode is attracting those electrons with this much force. Okay? And then your anode is losing electrons with this much force. So those forces together create your overall or standard voltage. Alright, so the question here is, what is the cell potential for a voltaic? That's another word for galvanic cell. It has nickel at one electrode and copper at the other. They're at 25 degrees Celsius and 1 molarity, so standard. Alright, so from the table they pulled the copper and the nickel, and these are the two reduction potentials. So based on this, which of these do you think will be reduced? The copper has the most positive cell potential, so it will be reduced. So there is the force with which it's going to attract those electrons. The nickel, however, is going to be oxidized. So we'll change the sign or subtract, whichever way you want to think about it. Don't change the sign and subtract, okay? You're either changing the sign or subtracting. I like to change my sign. And then we'll put them together to figure out the overall force. So 0.59 volts would be my overall force from the copper being reduced, because it has the greatest reduction potential, and then the nickel is going to be oxidized instead. So that's why I flip the sign on the nickel or subtract it. Overall, that'll give me 0.59 volts. Okay, you see that there on this slide. You can pause and read through that if you need to again. An important note at the bottom says that because we get a positive voltage, that means the reaction is a thermodynamically favored process. Alright, so if your voltage turns out to be positive, then that's thermodynamically favorable. That means that your delta G is negative, and your K, we got to put all these pieces together, is greater than 1. Alright, what if we have a standard cell? So this is an important note again. We know we're at 25 degrees Celsius and 1 molarity and 1 atmosphere. If we have any gases, we have silver nitrate and solid nickel. Now, silver nitrate tells me that I have silver ions, because nitrate is just going to be a spectator. So I have silver ions, and then I have solid nickel. It didn't say anything about nickel ions, but solid nickel is in this reduction potential. So I pulled both of these off the chart. Now, which of these is going to be reduced? The silver ion or the nickel ion? Well, first note, I don't have any nickel ion, right? I only have silver ion. So I know just from that that the silver is going to be reduced. However, if I did have nickel ion, the silver still has a greater reduction potential. So the silver is being reduced. Then the nickel is going to be oxidized. So this would be flipped over to make that nickel solid my reactant. Okay, and that's good because I have nickel solid, so I need it to be a reactant. So this whole thing's getting flipped around. Those are going to be your products now. When I do that, I'm going to make my reduction potential for nickel positive instead of negative, because it's now being oxidized. So altogether, I'll have a 1.05 volt system. So notice this combination of silver and nickel will make a better battery than that last combination we saw, because it has a higher voltage. Okay, so you see there again, they flip the sign on the nickel, put those together to get the overall voltage of the system. Alright, Now, let's figure out what the reaction would read if we wanted to put those two together. So here's our two reactions just from the reaction chart. Silver gaining an electron to become silver solid, nickel gaining 2 to become nickel solid. But we said the nickel is going to be oxidized. So we're going to flip the nickel around, which you see right here. And then we're going to try to put them together. Now the only problem is the silver is gaining 1 electron while the nickel is losing 2. So how do we balance that? You always have to have the same number of electrons being lost and gained. So in order for the silver's electrons to balance with the nickel, I'm going to multiply the whole silver reaction by 2. So that's going to make 2 silvers, 2 electrons, and 2 silvers. And you see that done on this top line. When you do that, that allows our electrons to cancel to then get our overall reaction. So here's our overall reaction down here at the bottom. However, when you do that, you do not multiply your voltages. Okay? You do not multiply your voltages. The reason is because voltage is based on the number of electrons. So if you doubled your electrons, you would also double your joules, and then they still would just cancel. So your voltage would still be the exact same value. If you double the electrons, you double the energy, or the joules, and then dividing that out gives you the same voltage. So when you double your reaction, which you have to do sometimes to cancel electrons, do not double that voltage when you do that. Alright, next question. We have a galvanic cell, and we have silver, and silver is being reduced. Okay, so we know that this is going on in the cell. They found that the cell potential was 0.47. This is for the whole thing. What is the reduction potential of the unknown metal? Okay, so what we're saying is we have some metal, we don't know what it is. It is on the other side of the cell from the silver. And it has some unknown potential value. Here's my question mark. Unknown, okay? So metal M plus an electron, we don't know what the voltage is, all right? It says the silver is reduced, so we know that this one stays 0.8. Now, whatever this other metal is, it has a reduction potential, right? That's what it's asking us for, the reduction potential. But this metal, this unknown metal, is not being reduced. They can't both be reduced, and it said the silver was being reduced. So the unknown metal is being oxidized, which means whatever value it had, that sign got flipped around. And then they put them together, and they ended up with 0.47 volts. So what goes with 0.80 to make 0.47? 0.80 minus what? Minus 0.33? Is that right? 0.33 volts. Okay, so 0.80 minus 0.33 volts would give me 0.47. So that means this unknown metal must have a potential of 0.33 volts. But I flipped it, right? I flipped it because it was being oxidized. So if I want to know what it was before I flipped it, then I'll have to make it positive, right? Because I flip it and make it negative, and that's how we get 0.47. So this unknown metal has a 0.33 volts as its potential. So we could then look at the chart and figure out what the unknown metal was. Okay, let's see how they work it out. So you can look at that one more time. We know that to find the overall potential, we do the cathode minus the anode, or cathode, change the sign on the anode. We know the overall was 0.47, and we know the cathode is 0.88. So they just rearranged this equation. They moved the anode over there to that side, and subtracted the total from both sides, so it's over here now. So now we're saying the anode is equal to the cathode minus the total. Notice they included their negative sign here to remind us that we're changing the sign on the anode. So then 0.80 minus 0.47 is 0.33 volts. They got a positive the first time they did it because they included their negative up here in their original equation. So the 0.33 volts is the reduction potential. When you change the sign on it and put it with the 0.80, you end up with your total. Okay, so you know it's 0.33 volts. Now to figure out what metal that is, we would need to look at a chart of our reduction potentials. I don't know if that 0.33 is on the chart they gave us, but we can look. Ooh, maybe. We got 0.33. It might be copper, because copper's is 0.34 volts. So that's plenty close enough. So it was probably copper was the unknown metal. Alright, so see how we figured that one out? Feel free to rewind, replay, slow-mo, fast forward, whatever you need to do as you look back over this material. There's only 2 lessons in this section, so we got to have this part down pat as we move into the next section on electrolysis, all right, and non-standard cells.